Swayam Prabha. Digital India. Educated India.
In the previous lecture, I introduced the concept of momentum and indicated how this conservation principle can make it easier to handle certain mechanics problems. We are going to take one more step in the direction of using conservation principles and work with energy conservation in this lecture. You have been hearing about work and energy maybe since your 10th, 11th grade. I am going to show you in this lecture how these concepts arise naturally when I try to eliminate the time from the equation of motion. Recall that the equation of motion is F is equal to m dv over dt, but at times it may so happen that I am not interested in the evolution of the system as a function of time. For example, if a particle is falling in the gravitational field of the earth, I may be interested in knowing what is its velocity at a certain height from the earth, and I do not have to really worry about time. In such situations, we eliminate time. And how do we do that? If I write F equals m dv dt, this is equal to, I can write as m dv dx dx dt. I am taking only one dimension into account right now. For 3-dimensional cases, we will see later what happens. So, F, let us take now only x direction, is equal to m d vx dt, which I wrote as m d vx dx dx dt, which is m vx dvx over dx, which is m over 2 d over dx Vx square. So, you see, I have now related the force directly to velocity, and there is no need to integrate over time. Let us see how it makes our problem solving slightly easier. Let me go back to the example of gravitational field, since I mentioned that earlier. Suppose I want to know the velocity of a particle in gravitational field. If the particle is moving in the radial direction, then I have dr dt is equal to the force which is in radial direction itself, which is minus g m over r square, or it should be d2r by dt square, because I am talking about the acceleration and the mass. And therefore, I have d2r over dt square as equal to minus g m over r square. This equation is very difficult to integrate with respect to time. On the other hand, let me apply the trick I used earlier in writing d2r dt square as d over dr dt times dr dt, and that gives me Vr d over dr Vr, and therefore, half d over dr Vr square is equal to minus Gm over r square. This is an equation which can be easily integrated with respect to r to obtain velocity as a function of the radial distance from the center or the height from the center of the from the surface of the earth. So, the need to eliminate t gives me a slightly different equation. Let me look at it slightly more carefully. So, I had written earlier f x equals m d v x over dt, and by transforming this into the form d over dx v x dx over dt, I got that f x is equal to 1/2 m d over dx v x square. If I integrate this equation, what I get is half m v x at some position x 2 square minus 1/2 m v at some position v x 1 square is equal to integration f x dx from position x 1 to x 2. Let us now interpret this equation. I am going to call this f x dx, the work done by the force. I am going to call this quantity 1/2 mv square the kinetic energy of the particle. So, what it tells me is that the change in kinetic energy is equal to the work done by a force. Not only have I defined the work and kinetic energy for you, I have also obtained a relationship between the two, in that the change in the kinetic energy of a particle is going to be equal to the work done by a force on it. Although I have taken a one-dimensional example, I will now generalize to a three-dimensional example. This is a statement in one dimension of the work energy theorem, which we use in solving mechanics problems again and again. Let us see now if I can generalize it to three dimensions. So, work done I had written as f x dx in one dimension. In three dimensions, the work done is going to be the force taken a dot product with dl integrated from point 1 to point 2. Let me explain this. Suppose a particle is moving from one position to some other position, from 1 to 2. I can break this path into small segments of dl each, and for each segment I calculate the work done, which is equal to the force in the direction of that segment times the length of that segment, and integrate. So, that gives me the work done by this force. Notice that I have to then know as to which path I am going over. So, this is the work done. Let us see if this can be related to the change in the energy or kinetic energy of the system. So, work which is equal to F dot dl can be written as m dv dt times dl, and when the particle is moving along a curve like this, dl is going to be v dt, and therefore, I have work is equal to integration m v dot dv, and this is nothing but integration m d v square over 2. When integrated over, it gives me work is equal to half m v final square minus 1/2 m v initial square, and the work as defined is F dot dl, moving over a curve from over a curve C from point 1 to point 2 is equal to delta K E. So, we have in general that the work done by a force is equal to change in the kinetic energy, and I am going to call this the work energy theorem. I emphasize again, when I calculate the work done, it is the work done by the force. Let me now ask a question, since I talked about a particle moving along a curve from one point to some other point. Is the work independent of the path, or does it depend on which path am I taking? So, if I calculate F dot dl from point 1 to point 2, is it the same whether I take this path or some other path or third path, or is it different? In general, the answer is that it could be different. The most simple example for this is the frictional force. Let us again take a one-dimensional example. Suppose I take a particle from point 1 to point 2, one directly and one take it to some other point and bring it back here. You can see that the work done by the frictional force in this case is going to be much larger than the work done by the frictional force in this case. So, in general, the work done by any force depends on the path taken. Let us take another example of this. Suppose there is a force field where the force applied is in circular direction. That is, if a particle is here, it will experience a force, now that you know planar polar coordinates, in phi direction. Let me then take a particle from point A to point B through two different paths. Path 1, let it be this one, A to B directly, and path 2, let it be like this, A to C and C to B like this. Let this point be C. In the first case, when I calculate F AB, it is in the direction of phi something, but the displacement dl is in direction dl r. So, F dot dl is 0, and therefore, work done A to B is equal to 0. How about work when I go from A to C to B? This is going to be work from A to C plus work from C to B. Work from A to C is like work from A to B, therefore 0, but this is not, because here the displacement and the force both are in phi direction. In fact, if F depends only on the radial distance, then work ACB is going to be the force at radius r times pi over 2 r, which is non-zero. So, if the particle moves in this force field from A to B through this path, by work energy theorem is going to have a kinetic energy at this point. On the other hand, if it moves along this point, there is going to be no change in the kinetic energy. So, this is another example of the force field where the work depends on the path taken. Let us see what happens if the work done is path independent. So, we have seen two examples of cases where the work depends on the path taken, but there are many forces in nature for which the work done is path independent. That is, no matter which path I take, whether I go from 1 to 2 along this path or this path or this path, the work done from 1 to 2 is going to be independent of path. An example of this is the gravitational field, the work done when two charges move due to their Coulomb interaction. In this case, if I go from 1 to 2 and come back via other path from 2 to 1, work done, since their magnitudes are equal, is going to be positive in one direction, negative in the other direction, and therefore in a closed path, work done is 0. So we have seen two cases. In one case, the work may depend on path, in the other case, work may not depend on path. For the cases where work is path dependent are known as non-conservative forces, whereas when work is path independent, these forces are known as conservative forces. So we just saw that frictional force is non-conservative. The force field like this is non-conservative. Gravitational force is conservative. These are important concepts. There are certain things I can do for conservative forces which I can't do for non-conservative forces, and that is precisely why I define these two classes. You will see later in your course in electromagnetism that this kind of E field or force field arises when magnetic field changes with respect to time.